Hi and welcome to Brook Abhiyantrics. In today's video, again we are going to talk about deflection of composite bars and also statically indeterminate structures, and also we are going to have a look of axial loads in interconnected structures. Right. So anyway, we'll start with the first problem here. The prismatic bar is fastened between two rigid walls AB and subjected to the total loads as shown in the figure below. Okay, so as they have said that the A and B is rigid walls, it means that the total deflection of AB will be equal to 0, right? So this deflection can be again divided into the deflection of, let me call this as A, and this would be B, and I'll call this particular section as C and this particular section as D, right? So the deflection of this particular body, deflection of this and deflection of this will totally be equal to 0, right? To solve this, first of all, let me now first draw the free body diagram of each individual parts of this. So for AC, the free body diagram would look something like this. So here the load would be, there is going to be a support, the support will be in tension, right? So this is RA and this is again will be equal to RA. So the length here is 100, right? So this is made up of copper, right? So the next one, the free body diagram of CD will be looking something like this, right? So here again we are going to have tension as well, which is RA minus 15.5, and again in the tension RA minus 15.5. So the length of this member is 200 mm. And finally for dB, again we are going to have something like this. So here we are going to have the direction of RB will be in compression, RB, and this will also be RB. Now the length of this particular member is again 300. This is also made up of copper. So second member was made up of steel, right? So we know all of these things. Let me just try to solve the problem. First of all, let me apply the static equilibrium. For the static equilibrium, I have a load here, so that is RA, support at A, and again we are going to have another load. Again this is also in this direction, RB. Now if I apply static equilibrium for this, I have RA plus RB, both of them are towards left direction, will be equal to 15.5 plus 34.5, which is nothing but 50 kilonewton, right? So this, I'll call this as equation number 1, right? So now since I'll make use of this particular equation, now delta is equal to 0 of delta of AB total will be equal to 0. Now this can be split into delta of AC plus delta of CD plus delta of DB will be totally equal to 0. Now if I substitute the formulas for this, for AC, that is the free body diagram of this, the load is RA into the length is 100 divided by the area, I'll take it as A, and the modulus of elasticity, I'll call this as EC, plus, and again this is also in tension, so plus I'll have RA minus 15.5 into the length is 200 divided by the area, I'll take it as A, and the material is steel, ES. Now for the third member we have compression meaning that the load will be negative, minus RB into the length is 300 divided by A into EC will be equal to 0. Now they've also said that, okay, I'll also assume that EC, yes, I'll know the value as 2 into 10 to the power of 5, and I also know the value of EC, that is 1.2 into 10 to the power of 5. So instead of using this, I'll just assume that ES by EC will be equal to 2. So I'm making this assumption. So if you want, you can just go with the known values, or you can simply take it as 2. Now if I substitute this, and again I'll have, first of all the area is cancelled out, so I can take the common and multiply to the RHS, and that will be 0, and again I'll have, and also I can divide the LHS by 100, so this is gone, this 2 is double zeros is gone, this double zero is gone. So now the remaining part is RA by EC plus RA minus 15.5 into 2 and divided by, instead of EC I'll write it as 2 into instead of ES I'll write it as 2EC minus RB divided by EC, and again EC will be cancelled here, will be equal to 0. Now if I also 2 is also getting cancelled. Now if I simplify this further, I'll have 2RA minus I have left out 3 here. I have minus 3RB is equal to 15.5. Now instead of RB I'll substitute. I know that from equation number 2 I can substitute as 50 minus RB. Now here 2 into 50 minus RB minus 3RB is equal to 15.5. Now if I simplify here, I'll have 100 minus 2RB minus 3RB is equal to 15.5. Now minus 5RB is equal to, if I send 100 to the other side, I'll have minus 84.5, and now RB will be equal to 84.5 divided by 5 will give me 16.9 kilonewton. So remember, this is in kilonewton. I have not substituted into 10 to the power of 5 here. Right, so now to find out RA, I'll have RA will be equal to 50 minus 16.9, which is nothing but 33.1 kilonewton. So now the reactions at the structures, reactions at the support A and B is found. Now moving on to the next question, we have a compound bar consists of a circular rod of diameter 25 mm. I'll write it as steel DS is given as 25 mm. Okay, is fitted rigidly into a copper tube of internal diameter 25. Okay, and the thickness is 2.5 mm. So I can write a schematic here. So let me assume this as steel rod, something like this, and now surrounding this we have a copper tube. Right, so they have given this thickness as 2.5 and this diameter is 25 mm. Right, so now the diameter of copper outer diameter of copper will be given by 25 plus 2.5 plus 2.5, which is nothing but 30 mm. Okay, and they've also, the bar is subjected to a load of, okay, so the bar is, I can just write this in a better way. So the bar is subjected to a load of 100 kilonewton. So P is given as 100 into 10 to the power of 3. Find the stresses developed in two materials. I'll have to calculate sigma S and I also have to calculate sigma C. Now let me calculate the areas individually. Now the area of steel, that is the inner rod, will be equal to pi by 4 into d square, that is 25 square, which is nothing but 490.8 mm square. Now if I calculate the area of copper, I'll have pi by 4 into 30 square minus 25 square. So outer diameter square minus inner diameter square. So which is nothing but this will give me 215.98 mm square. Now ES elastic modulus of elasticity of steel is given as 2 into 10 to the power of 5 Newton per mm square, and elastic modulus of copper is given as 1.2 into 10 to the power of 5 mm square. Right, so now with all of these things, I will assume the load taken up by the steel as PS and I'll take the load taken up by the copper as PC. Now if I write a free body diagram, I'll have something like this. Sorry, not the free body, instead here the support will be given as, we'll have PS here and the PC will be all throughout the tube, so I'll have PC. So now if I apply the static equilibrium, I'll have PS plus PC will be given as total P. Now I'll call this as equation 1, and also the delta, right? So since they are fixedly what is the word that they have used is rigidly fitted, right? So meaning if one of the tube is moving, if the one of the tube is deflecting, the other tube will also deflect by the same amount. So this is another way of saying delta S is equal to delta C. right? So here if I apply the formula here, I'll have PS into L, since the length are same. Again I'll have AS into ES is equal to PC into L divided by AC into EC. Now the length is cancelled out, right? So if I have, now I can write it as PC by PS will be given as, if I substitute all the values, I'll have 215.98 into 1.2 into 10 to the power of 5 divided by 490.87 into 2 into 10 to the power of 5. Now if I simplify this, I'll get 0.264 as the answer. Now if I substitute this back in equation 1 will be becoming 0.264 PS plus PS will be equal to P. Now which is nothing but PS will be given as P, the value of P as 100, that is 100 kilonewton divided by 1.264, which is nothing but 79.11 kilonewton. Now for PC, I'll have 100 minus 79.11, which is nothing but 20.89 kilonewton. Now for the stresses, I can directly calculate sigma S is given by PS divided by AS, so which is nothing but PS is 79.11 divided by the AS is 490.87, so which gives me the answer 0.161 kilonewton per mm square. Now for sigma C, I can write it as PC by AC, which is nothing but 20.89 divided by 215.98, which is nothing but 0.097 kilonewton per mm square. Right, so fairly straightforward question. Let me move to the next question now. Right, so for the prismatic bar shown below, find the reactions at A and B, and also I have to find out, I'll simply write it down, RA, I'll have to calculate RB, and deflections of C. Okay, I'll have to calculate with respect to A, so I'll have to calculate delta AC. Right, so also we have to plot the axial thrust diagram. So to draw this, I'll have to calculate all the forces acting, so that is nothing but the reaction forces here. Right, so for this, let me first draw the free body diagram here. So for the free body diagram, I'll have similar to this, A, B, and I'll have C somewhere here. Right, so here I have a force which is acting here. I'll call it as P, and now this particular length I'll call it as, they have given it as A, and this particular length is B. Now here we have a force which is opposite to P, that is RA, and here again we'll have a support reaction which is opposite to the applied load, that will be RB. Now if I apply the static equilibrium, I'll have RA plus RB will be equal to P. I'll call this as equation number 1. Now moving on to the since the A and B are a fixed support, so the total delta AB will be equal to 0. Delta AB can be split into delta AC, we'll be having tension here, and plus delta CB, here we'll be having compression, will be equal to 0. Now if I write the individual free body diagram for this, we'll have, this will be A, and this will be RA, and this will be RA again. Right, so now here if I write the free body of the other part here, so this length will be B, and here we'll have RB, and here also we'll have RB. So instead of RB, I can also write it as RA minus P, so which is equal to RA minus P. So from the equation 1. Right, so now if I apply the formulas for this, I'll have for AC, which is this free body diagram, I'll have RA into the length is A, sorry, this is capital A, sorry, RA into small a divided by the area into E. Now minus RB, because this is in compression, mind you, RB into the length B divided by A into E will be equal to 0. Since the area and the material are same, we can cancel them out. Right, so here I'll have RA into RA minus B into P minus P minus RA, right? So whole divided will be equal to 0. Now A into RA minus BP plus BRA will be equal to 0, which is nothing but A plus B into RA mine is equal to B into P. Now note that A plus B is nothing but L. So I'll simply call it as the length of the bar L. For sake of simplicity, I'll have RA will be given as BP divided by L. Now to calculate RB, I'll make use of the equation number 1. RB will be equal to P minus RA, so which is nothing but P minus BP by L, so which is nothing but so L is nothing but A into B, that is AP plus BP minus BP whole divided by L, so which is nothing but AP by L. So this is RB, right? So now if I want to calculate the delta AC, I will be simply substitute these values, so which is nothing but RA into A divided by AE. So here RA is nothing but BP into A divided by LAE. So this will be the deflection of delta AC, right? So also for the stress the axial force diagram, so I'll simply mark A, C and B. Now here for AC it is under tension, it will be positive. The value is ABP divided by LAE, so which is nothing but RA, right? So here I'll have RA value. Now here this is plus, and now we'll have, because CB is under tension, sorry, compression, we'll have negative. This value will be given as, sorry, the RA value is BP by L, so this will be equal to RB, so which is nothing but AP into L, AP by L, right? So this finishes this problem. Let me move on to the next one. Right, so a load P is supported by a system of 3 rods as shown below. The outer rods are identical and are made up of same material, so meaning that E1 is equal to E3. While the inner rod is of different material, so we have E2. Determine the forces in the rods. Hence, if P is equal to 30, so we have another load here. So this is P. If P is 30 kilonewton and theta is equal to 30 degree, determine these forces. Okay, so we'll also have to take out E1 by E2 is equal to 2. Now with this, first of all, these cannot be individually solved with static equilibrium, so we'll also have to use some compatibility equations. So here the compatibility equations will be getting from the displacement diagram. So first of all, we'll have to write the displacement diagram for this. Now first of all, since let me just point out O. Now how does this O move? So this point will be coming down because of the load P, right? So here I'll have O dash, right? So this particular member 2 is going to be elongated because of the load, so this O will be moved down to O dash, right? So now what will happen to the member 3? Member 3 is again under tension, right? So here instead this is going to first extend. Here we have the third member somewhere here, right? So first of all, this is going to extend and we are going to drop a perpendicular from O dash, right? So this is going to be the new positions for C1, right? So for the member 1, again this is going to elongate in this particular direction. Again I'll drop a perpendicular to this. I'll have the displacement diagram something like this. This is going to be the new A1. So here the OA1 is nothing but the deflection of the member 1, and this OC1 will be the deflection of member 2, right? I'll call this as delta 1. I'll call this particular O dash will be as delta 2, and I'll call OC1 as delta 3, right? So O delta 1 will be equal to the elongation of delta OA, right? So delta 3 will be nothing but the elongation in the member 3, that is delta OC, and so delta 2 will be nothing but the elongation of the member 2, that is delta OB. Now with this particular information, the angle between this particular two things is theta, and this is also theta. Now with this particular information, we can write down the different equations. Now first of all, let me apply the static equilibrium for this. So now what are the different loads here? First of all, I have the P load and I have the load taken by the member 3. I'll call this as P1 again. Here I'll have the load taken up by member 1. So I'll call this as again P1 because these two are identical, right? So I can write this as P1 only. Now I'll also have the load taken up by the middle member. So I'll write this as P2. Now if I write the free body diagram, I'll have they have also given these two angles as theta and theta. Now if I apply static equilibrium for this, I'll have P is equal to P2 plus P1 cos theta plus P1 cos theta. So which is nothing but P2 plus 2 P1 cos theta. Now I'll call this as equation number 1. And now also, what about from the displacement diagram, I can write delta 2 cos theta will be equal to delta 1. So here this member delta 2 into cos theta will be given by delta 1, right? So now if I apply the formulas for this, delta 2 is nothing but P2 into L2 divided by A2 into E2 into cos theta is equal to P1 L1 by A1 E1. Now so from I'll again make use of some properties of this. So if I consider this triangle OAB, right? So if I consider this, so this is a right angle triangle, right? So here in triangle OAB, I have, if I consider cos theta, I'll have OB divided by OA. So which is nothing but, OB is nothing but the length of member 2 and OA is nothing but the length of member 1. So this will be nothing but cos theta, right? So here I have L2, I'll also have L1. If I send this to the left hand side, I'll have L2 by L1. Instead of that, I can write P2 into cos theta into cos theta, I'll have cos square theta divided by A2 into E2, which is nothing but, which is equal to P1 divided by A1 E1. Now they have also given the ratio of E1 by E2, and if I send this E1 to the LHS, again I'll have P2 into 2 cos square theta divided by A2. Now I'll assume that A1 is equal to A2. Now for the sake of simplicity, I have assumed that I can simply cancel these two out. 2P2 cos square theta is equal to P1. Now what will be the value of P1? So again I'll so now P1 will be equal to 2 cos square theta into, instead of P2 I'll write P minus 2 P1 cos theta, right? So I'll just make use of equation number 1 here, right? So now if upon simplifying, P1 will be given as P1 will be given as 2 cos square theta into P minus 4 cos cube theta into minus 4 cos cube theta into P1. So now finally P1 will be given as 2 cos square theta into P divided by 1 plus 4 cos cube theta. Now if I substitute the value of theta and I simplify that, so P is given as 30 kilonewton and theta is given as 30 degree. Now if I substitute these two, the P1 value will be given as 12.5 kilonewton. Okay, now upon substituting this value in equation number 1, again I'll have P2 will be given as 8.34 kilonewton. Right, so this finish up this problem. Let me move on to the last problem in this video. Now here again I have 3 identical pin connected bars are arranged as shown in figure and support A load P. Find the axial force in each bar and also the vertical displacement at point of application of load. So I'll have to find out the vertical displacement, so which is nothing but the deflection in OC. So I'll have to find out the deflection in OC. neglect the possibility of any lateral buckling of the bar. All the bars are of the same length, so meaning the length is same and also the same cross-sectional area. Okay. Right, so now we have, again I'll write down a simplified version of all the loads taken here. Now first of all, I have at point O, I have load P, and also I have some reactions here, right? The load taken up by the reaction force by, or the load taken up by OB, I'll call this as P1, and again I'll take up a load acting upon member OC, again I'll call this as P2, and again there is going to be another load, again that will be P1 again, right? So now I'll call this as 1, 1, and I'll call this as 2. So what exactly is happening here? The member OB and OA are both in tension. I'll just call it as plus, and this OC will be in compression. So that is why I've called this as P1 and P1, this is P2. Right, so now if I apply the static equilibrium for this, again P is equal to P2. So what is this angle? So this angle is 120 degree. So meaning, so here this is also 120 degrees, half of this is 60 degrees now, plus P1 cos 60 plus P1 cos 60. So which is nothing but P2 plus P1. So this will be our equation number 1. So again now I'll have to write down the displacement diagram. Right, so first of all, let me consider point O here. The point O will move down because of point P. So the member 2 is going to get compressed. So this is going to be the new O dash, and this particular length is our deflection of OC. I'll call this as delta 2. Now what will happen to the member OB? Member OB will move in this direction, and we'll have something like this. This is going to be our new B1, and this particular deflection is nothing but delta 1. That is equal to delta OB. And again similarly in the opposite direction, this is a perpendicular one, and also here we will be having new A1, and this will be again delta 1. Again that will be equal to delta OA. Right, so this angle is 60 degrees. Fine, with this knowledge we can write delta 2 is equal to, delta 1 is equal to delta 2 into cos 60. So which is nothing but half into delta 2. I can apply the formula for delta 2, which is nothing but P2 L by AE. So I'll also apply the formula for delta 1, that is P1 L by AE. So L, A and E will get cancelled. So we can write P2 is equal to 2 P1. So I'll call this as equation number 2 and apply this equation number 2 in equation number 1. Equation 1 will become P1 plus 2 P1 is equal to P. So P1 will be equal to P by 3. Now P2 will be equal to P minus P by 3, that is nothing but 2P by 3. Right, so the deflection of O2, the vertical displacement, that is nothing but delta 2 is equal to P2 L by AE. So if I simply apply the P2 value, that is 2PL divided by 3A into E. So this is the vertical displacement of point O. Right, so hopefully this video has been helpful for you. See you guys in the next video. Thank you. Bye bye. Happy learning.